Next up, we're looking at to match or not to match, revisiting image matching for reliable visual place recognition. So, visual place recognition, or VPR, which is about an AI identifying where a photo was taken, traditionally used two steps. First, get initial image candidates, then use image matching, a process that closely compares image features to re-rank them. But this paper asks if that second re-ranking step is always helpful with modern AI, or if it can sometimes degrade results. Alright, and for those of you who like to get your hands dirty, the researchers have actually made their code available on GitHub. It's a PyTorch implementation, which is a popular framework for building AI models. So you can find their whole visual place recognition pipeline there, including the image matching and re-ranking parts, and even their uncertainty evaluation tools. Okay, so this first figure, figure 1, really sets the stage for their investigation. It shows how the performance, specifically something called recall at 1, which measures how often the system's very first suggested image is the correct one, has changed over the years from 2016 to 2024. We see two lines, pure retrieval in red and retrieval plus re-ranking in blue. On the left, for the PITS 30K dataset, pure retrieval now actually outperforms re-ranking with the latest methods. But on the right, for the more challenging SFXL occlusion dataset, re-ranking still provides a clear benefit. This visual really underscores the paper's core question about when that re-ranking step is truly useful. Alright, so building on what we saw about when re-ranking helps, Figure 2 now gives us a visual of how this re-ranking pipeline actually works. You start with a query image, that's the photo you want to find the location of, and a database of known images. A retrieval method then pulls out an initial candidate shortlist. Here you can see the second candidate, highlighted in green, is the correct match initially. Then, an image matching method meticulously compares the query to each of these candidates, counting inliers, which are essentially corresponding points or features that align well between two images. Finally, these candidates are re-ranked based on these inlier counts, and you can see in this example, the correct image has now moved to the top spot. So, while the previous figure showed re-ranking working perfectly, Figure 3 illustrates a scenario where this image matching step can actually go wrong. On the left, we see the query image and its correct match, the positive, which was initially the top retrieved image. Using superglue paired with random sample consensus, or RAN-SAC, which is an algorithm that helps filter out incorrect feature matches, it only found 7 inliers. But on the right, the query compared to an incorrect image, a negative, found 26 inliers. So in this case, re-ranking based on inlier count would mistakenly promote the wrong image. Okay, so to really dig into when re-ranking helps and when it might hurt, as we saw in that last example, the researchers used a wide variety of image collections, or datasets. Table 1 here lays them out. It details the number of query and database images, the type of scenery, like indoor or urban scenes, and importantly, the domain shift for each. Domain shift describes the kinds of challenges present, such as significant viewpoint changes, occlusions, where objects are partly hidden, or shifts from day to night. We see some datasets, like PITS 30K, have no major domain shift, while others, like SFXL occlusion, are designed to be tough. Alright, now that we've seen the variety of datasets used, Figure 4 gives us a practical look at the different re-ranking methods themselves, specifically how they balance accuracy against speed. On the vertical axis, we have mean recall at 1, which again is how often the very first image suggested by the system is the correct one, averaged across all those datasets. And on the horizontal axis, we have mean latency, which is just a fancy way of saying how long in milliseconds it takes to process each query image. So ideally, you want a method in the top left, high accuracy and low processing time. Each dot on this plot is a different image matching method used for re-ranking, and you can see they're all over the place, showing there's often a trade-off. Okay, so after seeing that accuracy versus speed plot from Figure 4, Table 2 here dives deeper into the actual performance numbers. It shows us the recall at 1 and recall at 1.0. So again, how often the correct matches in the top 1 or top 10 results for many different re-ranking methods across all those datasets. That very first row of results, the one labeled with just a dash, shows the performance of the initial megalock retrieval before these specific image matching methods are applied for re-ranking. What's really telling is that on datasets where megalock is already doing great, like PITS 30K, where its initial recall at 1 is 94.1%, many re-ranking methods actually lower this score. But on tougher datasets like SFXL-Night, where megalock's initial recall at 1 is 52.8%, methods like MatchFormer, which gets up to 61.8%, provide a clear improvement. So building on those performance numbers from Table 2, where we saw re-ranking wasn't always helpful, Figure 6 gives us a visual on why. This is a histogram, which is a type of bar chart, showing how data is distributed across different ranges. Here, it's plotting the probability that a query image will be wrongly localized, meaning its top predicted match is actually more than 25 meters away. The vertical axis shows normalized counts, essentially the proportion of queries. For PITS 30K in blue, that very tall bar on the left shows most queries have a very low probability of being incorrect. But for the tougher SFXL occlusion dataset in red, the probabilities are more spread out, indicating greater uncertainty. These probabilities are calculated using logistic regression, a statistical method for predicting likelihoods, trained on uncertainty scores from the MAS3R image matching method. That histogram really drives home the point that just blindly re-ranking isn't always the best move. The big takeaway, I think, is that understanding the uncertainty in that initial match is crucial for deciding whether more processing will actually help improve localization. This work is important because it guides us toward more robust and efficient visual place recognition, which is vital for things like self-driving cars. Well, that's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.